The beginning and cosmic inflation. In the beginning there was nothing. No time, no space, no matter. Only silence. Deep, eternal silence. Then, in a fraction of a second, everything changed. From a point smaller than an atom, hotter than we can imagine, the universe was born. This was not an explosion in space. It was the rapid expansion of space itself. Around 13.8 billion years ago, in less than a trillionth of a second, the universe grew from a singularity to the size of a galaxy. With that came the birth of time and the laws of physics. Gravity emerged, and electromagnetism took form. Moreover, the strong and weak nuclear forces, the invisible threads that weave the fabric of the cosmos, began their eternal work. The universe was young, wild, and unimaginably hot, a sea of raw energy. First particles, light, and the cosmic fog. As the newborn universe expanded, energy transformed into matter. Particles appeared as tiny quarks and gluons, spinning and colliding in a high-energy dance. These quarks formed protons and neutrons. Moreover, after just a few minutes, the first atomic nuclei, mostly hydrogen and helium, were born. However, the universe remained dark. For nearly 400,000 years, light could not escape. It was trapped in a thick, hot fog of charged particles, scattering endlessly. Then came a turning point. Atoms captured their electrons. The fog lifted. Moreover, for the first time, light traveled freely across the cosmos. This first light, the cosmic microwave background, still echoes across the universe today. A silent fingerprint of creation. It tells us, we were there. We were part of that beginning. Galaxies, Earth, and our place in the cosmos. Over billions of years, gravity shaped the early chaos into order. Galaxies spun into existence. Stars ignited. Some lived and died in magnificent explosions, forging heavier elements in their final breaths. From their ashes, new stars were born, with planets orbiting around them. Moreover, in one quiet spiral galaxy, one ordinary star gave birth to something extraordinary. Our Sun, our solar system, our Earth. From the dust of ancient stars came oceans, mountains, and eventually, life. Moreover, from life came we, curious creatures, looking up at the stars, asking where it all began. The answer? It began here, with the Big Bang. It is not just a theory, it is the origin of everything. The story of stars, galaxies, planets, and you. We are made of stardust. The universe gave us its breath. Moreover, it still expands silently, endlessly, beautifully. From silence came light. From light came stars. And from the stars, us. Here is what Stephen Hawking's final paper was actually about. Spoiler, it is not the end of the universe, and it is not likely to lead to new evidence for the multiverse either. On March 14th, 2018, the renowned scientist Stephen Hawking, one of the most celebrated figures in human history, passed away at the age of 76. He left a rich legacy in the fields of astrophysics and cosmology, sharing the wonders of the universe with not only his colleagues but also the general public. Best known for his work on black holes, general relativity, the topic of singularities, and the famous type of radiation that bears his name, Hawking radiation, his final legacy to humanity, comes in the form of a scientific paper still under peer review. While the most significant contributions Hawking made to theoretical physics occurred in the early stages of his career, in the 1960s and 1970s, he continued to work on topics ranging from the black hole information paradox to the firewall problem and the origin of space and time itself. His final paper, entitled a smooth exit from eternal inflation, focuses on the birth of the universe as we know it. Maybe Big Bang may not be the beginning of everything, new theory suggests. The Big Bang is often described as the explosive birth of the universe, a singular moment when space, time, and matter sprang into existence. However, what if this was not the beginning at all? What if our universe emerged from something else, something more familiar and radical at the same time? In a new paper published in Physical Review D, our calculations suggest that the Big Bang was not the start of everything, but rather the outcome of a gravitational crunch or collapse that formed a very massive black hole, followed by a bounce within it. This idea, which we refer to as the black hole universe, presents a radically different perspective on cosmic origins, yet it is grounded entirely in established physics and observations, today's standard cosmological model based on the Big Bang. And cosmic inflation, the idea that the early universe rapidly blew up in size, has been remarkably successful in explaining the structure and evolution of the universe. However, it comes at a price. It leaves some of the most fundamental questions unanswered. For one, the Big Bang model begins with a singularity, a point of infinite density where the laws of physics break down. This is not just a technical glitch, it is a deep theoretical problem that suggests we do not understand the beginning at all. To explain the universe's large-scale structure, physicists introduced a brief phase of rapid expansion in the early universe, known as cosmic inflation, powered by an unknown field with unusual properties. Later, to explain the accelerating expansion observed today, they added another mysterious component: dark energy. In short, the standard model of cosmology works well, but only by introducing new ingredients we have never observed directly. Meanwhile, the most basic questions remain open. Where did everything come from? Why did it begin this way? Moreover, why is the universe so flat, smooth, and large? Our new model addresses these questions from a different angle, by looking inward rather than outward. Instead of starting with an expanding universe and trying to trace back how it began, we consider what happens when an overly dense collection of matter collapses under gravity. This is a familiar process. Stars collapse into black holes, which are among the most well-understood objects in physics. However, what happens inside a black hole, beyond the event horizon from which nothing can escape, remains a mystery. In 1965, the British physicist Roger Penrose proved that under very general conditions, gravitational collapse must lead to a singularity. This result, extended by the late British physicist Stephen Hawking and others, underpins the idea that singularities like the one at the Big Bang are unavoidable. The idea helped win Penrose a share of the 2020 Nobel Prize in Physics and inspired Hawking's global bestseller, A Brief History of Time, From the Big Bang to Black Holes. However, there is a caveat. These singularity theorems rely on classical physics, which describes ordinary macroscopic objects. If we include the effects of quantum mechanics, which rules the tiny microcosmos of atoms and particles, as we must at extreme densities, the story may change. We show that gravitational collapse does not have to end in a singularity. We find an exact analytical solution, a mathematical result with no approximations. Our maths shows that as we approach the potential singularity, the size of the universe changes as a hyperbolic function of cosmic time. This simple mathematical solution describes how a collapsing cloud of matter can reach a high-density state and then bounce, rebounding outward into a new expanding phase. However, how come Penrose's theorems forbid such outcomes? It all comes down to a rule called the Pauli exclusion principle, which states that no two identical particles known as fermions can occupy the same quantum state. We demonstrate that this rule prevents the particles in the collapsing matter from being squeezed indefinitely. As a result, the collapse halts and reverses. The bounce is not only possible, but also inevitable under the right conditions. Crucially, this bounce occurs entirely within the framework of general relativity, which applies on large scales such as those of stars and galaxies, combined with the basic principles of quantum mechanics. No exotic fields, extra dimensions, or speculative physics are required. What emerges on the other side of the bounce is a universe remarkably like our own. Even more surprisingly, the rebound naturally produces the two separate phases of accelerated expansion, inflation and dark energy, driven not by hypothetical fields, but by the physics of the bounce itself. Testable predictions. One of the strengths of this model is that it makes testable predictions. It predicts a small but non-zero amount of positive spatial curvature, meaning the universe is not exactly flat, but slightly curved, like the surface of the Earth. This is simply a relic of the initial small overdensity that triggered the collapse. If future observations, such as the ongoing Euclid mission, confirm a small positive curvature, it would be a strong hint that our universe did indeed emerge from such a bounce. It also makes predictions about the current universe's rate of expansion, something that has already been verified. This model does more than fix technical problems with standard cosmology. It could also shed new light on other deep mysteries in our understanding of the early universe, such as the origin of supermassive black holes, the nature of dark matter, or the hierarchical formation and evolution of galaxies. These questions will be explored by future space missions such as Arrakis, which will study diffuse features such as stellar halos, a spherical structure of stars and globular clusters surrounding galaxies, and satellite galaxies, smaller galaxies that orbit larger ones, that are difficult to detect with traditional telescopes from Earth and will help us understand dark matter and galaxy evolution. These phenomena might also be linked to relic compact objects, such as black holes, that formed during the collapsing phase and survived the bounce. The black hole universe also offers a new perspective on our place in the cosmos. In this framework, our entire observable universe lies inside the interior of a black hole formed in some larger parent universe. We are not special, no more than Earth was in the geocentric worldview that led Galileo, the astronomer who suggested the Earth revolves around the Sun in the 16th and 17th centuries, to be placed under house arrest. We are not witnessing the birth of everything from nothing, but rather the continuation of a cosmic cycle, one shaped by gravity, quantum mechanics, and the deep interconnections between them. From Enrique Gastanaga, professor at the Institute of Cosmology and Gravitation, University of Portsmouth. The standard model of cosmology assumes that our universe began 13.8 billion years ago from a singular Big Bang creation. This can explain a vast range of different astrophysical data, from a handful of free cosmological parameters. However, we have no direct evidence or fundamental understanding of some key assumptions: inflation, dark matter, and dark energy. Here, we review the idea that cosmic expansion originates not from gravitational collapse and bounce, but rather from a different mechanism. The collapse generates a black hole, BH, of mass m scheme C5x10 that formed 25 year ago. As there is no pressure support, The cold collapse can continue inside in free fall until it reaches atomic nuclear saturation, GeV, which quantum mechanics halts, as two particles cannot occupy the same quantum state. The collapse then rebounds, much like a core collapse supernova, triggering the expansion of the Big Bang. Cosmic acceleration results from the black hole event horizon. During collapse, perturbations exit the horizon to re-enter during expansion, giving rise to the observed universe without the need for inflation or dark energy. Using Occam's razor, this makes the BH universe, BHU model, more compelling than the standard singular Big Bang creation. Hubble pinpoints record-breaking explosion. Peering across 7.5 billion light-years and halfway back to the Big Bang, NASA's Hubble Space Telescope has photographed the fading optical counterpart of a powerful gamma-ray burst that holds the record for being the intrinsically brightest naked-eye object ever seen from Earth. For nearly a minute, this single star was as bright as 10 million galaxies. Hubble Wide Field and Planetary Camera 2, WFPC-2, images of GRB 80319b, taken on Monday, April 7th, show the fading optical counterpart of the Titanic blast. The object erupted in a brilliant flash of gamma rays and other electromagnetic radiation at 2:12 a.m. EDT on March 19th and was detected by SWIFT, NASA's Gamma Ray Burst Watchdog satellite. Immediately after the explosion, the gamma ray burst glowed as a dim fifth magnitude star in the spring constellation, Bootis. Designated GRB EA13b, the intergalactic firework has been fading away ever since then. Hubble astronomers had hoped to see the host galaxy where the burst presumably originated. However, they were taken aback that the light from the GRB is still drowning out the galaxy's light even 3 weeks after the explosion. This is particularly surprising, given that it was initially such a bright GRB. Previously, bright bursts have tended to fade more rapidly, which fits into the theory that brighter GRBs emit their energy in a more tightly confined beam. The slow fading of the leaves puzzles astronomers about the source of energy that powered this GRB, making Hubble's next observations of this object in May all the more crucial. Called a long-duration gamma-ray burst, such events are theorized to be caused by the death of a very massive star, perhaps weighing as much as 50 times our Sun. Such explosions, sometimes dubbed hypernovae, are more powerful than ordinary supernova explosions and are far more luminous, in part because their energy seems to be concentrated into a blowtorch-like beam that, in this case, was aimed directly at Earth. The Hubble exposure also reveals field galaxies surrounding the fading optical component of the gamma-ray burst, which are likely unrelated to the burst itself. Hubble spies Big Bang frontiers. Observations by the NASA ESA Hubble Space Telescope have utilized gravitational lensing to unveil the largest sample of the faintest and earliest known galaxies in the universe. Some of these galaxies formed just 600 million years after the Big Bang and are fainter than any other galaxy yet discovered by Hubble. The team, for the first time with some confidence, has determined that these small galaxies were vital to creating the universe that we see today. An international team of astronomers, led by Hakim Atek of the École Polytechnique Fédérale de Lausanne, Switzerland, has discovered over 250 tiny galaxies that existed only 900 million years after the Big Bang, making it one of the largest samples of dwarf galaxies yet discovered at these epochs. The light from these galaxies took over 12 billion years to reach the telescope, allowing the astronomers to look back in time when the universe was still very young. Hubble observations have leveraged gravitational lensing to unveil the largest sample of the faintest and earliest known galaxies in the universe. Some of these galaxies formed just 600 million years after the Big Bang. Although impressive, the number of galaxies found at this early epoch is not the team's only remarkable breakthrough, as Johann Richard from the Observatoire de Lyon, France, points out. The faintest galaxies detected in these Hubble observations are fainter than any other yet uncovered in the deepest Hubble observations. By examining the light emitted by galaxies, the team discovered that the accumulated light from these galaxies could have played a significant role in one of the most mysterious periods of the universe's early history, the epoch of reionization. Reionization began when the thick fog of hydrogen gas that had cloaked the early universe started to clear. Ultraviolet light was now able to travel over larger distances without being blocked, and thus the universe became transparent to ultraviolet light. By observing the ultraviolet light from the galaxies identified in this study, astronomers were able to determine whether these were, in fact, some of the galaxies involved in the process. The team determined that the smallest and most abundant of the galaxies in the study could be the major actors in keeping the universe transparent. By doing so, they have established that the epoch of reionization, which ends when the universe is fully transparent, occurred approximately 700 million years after the Big Bang. In a paper appearing in the Astrophysical Journal, lead author Atek explained, "If we took into account only the contributions from bright and massive galaxies, we found that these were insufficient to reionize the universe. We also needed to add in the contribution of a more abundant population of faint dwarf galaxies." To make these discoveries, the team utilized the deepest images of gravitational lensing available to date, which were taken as part of the Hubble Frontier Fields program, covering 3 galaxy clusters. These clusters generate immense gravitational fields that can magnify the light from faint galaxies, located far behind the clusters themselves. This enables the search for and study of the first generation of galaxies in the universe. Jean-Paul Kniep, co-author of the study from the École Polytechnique Fédérale de Lausanne, Switzerland, explains, clusters in the frontier fields act as powerful natural telescopes and unveil these faint dwarf galaxies that would otherwise be invisible. Co-author of the study, Mathilde Jozak from Durham University, UK, and the University of KwaZulu. Natal, South Africa, remarks on the significance of the discovery and Hubble's role in it. Hubble remains unrivaled in its ability to observe the most distant galaxies. The sheer depth of the Hubble frontier field data guarantees an exact understanding of the cluster magnification effect, allowing us to make discoveries like these. These results highlight the impressive possibilities of the Frontier Fields program, with more galaxies at even earlier times likely to be revealed when Hubble peers at 3 more of these galaxy clusters shortly.